Sure.
Awesome.
Hey guys, nice to meet you. I'm Stefan.
Welcome.
Welcome, Dave.
Welcome, Stefan.
I'm Dave. Hi.
Yeah.
Hi Dave.
How do I make this go?
In the upper right-hand corner, it says view. I think you could change it there.
Yeah, I'm looking
We
for
can
that.
see you just fine.
Oh, that's always great. I'm just here to be seen anyway. How do you get like the grid view? I don't see the thing.
That will come up. I think once Spencer is not sharing the screen that we see right now with our logo.
You can't see everybody.
Oh, okay. All right.
And then once he's stopped sharing the screen, then it becomes an option.
Gotcha.
On the right hand side of where you see the logo, there's a couple little bars there. If you grab that, you can slide it left and right and expand the screen. If that's what you're looking. Oh yeah.
You can hit the down arrow to scroll through people on the right side.
I can't help you.
Hey, Gilchrist.
Yes.
Gilchrist, what's the temperature out in Arizona today?
Well, I don't know. I'm in Monterey Park right now.
I thought you were back in Arizona. I thought you were gone. Okay.
No. I was gone, but I'm still working for the pipe organ company, so I have things to do. I've been here for. I go back to Arizona on Friday. Not quite certain exactly when I'm coming back, but I've got some things to take care of, family issues stuff to take care of in Cayman. And then I come back.
Okay.
I was in Palm Desert today from 11 to 12, and it was 111.
Wow. Yeah. Oh, it's cool.
I was there Saturday. I was there Saturday, and just about the same time it was 116.
Yeah.
Yeah, I just heard from my parents down in Tucson, and it was 111 today. So
yeah.
Wow.
That's pretty typical for those places.
Death Valley 130.
I actually heard a news report today that I don't understand, because they swear that it was 134 yesterday, which matches their all-time high from the 30s.
Wow.
That wasn't the official.
That's what I couldn't figure
Well,
out. It was on the news. I was questioning it because I thought the official was 131, but
Everything on the news is true.
The weather stations that I can get at, and there's only a couple out there, one in Stovepipe Wells and one in Furnace Creek, that topped out around 128 or 29, but they're not the official stations. They've got the one out front in the visitor center that everybody thought said 135, which it did, but that thermometer is actually in the sun. So it measures consistently a lot higher than around it, like 4 or 5 degrees or something. So I doubt that it made it to 134, 130, I believe, but I'm not so sure about 134.
The 134 was 1913, and it is disputed because other readings in the area didn't get that high, but it was still recognized as an official record, although there's still some controversy on that. The 130 is the officially recognized temperature, and that one is that I think 2020 actually was the last time that the 130 was recorded, and we did match that not yesterday but Saturday.
Yeah.
And so 130 is officially recognized without dispute. 134 is officially recognized, but because it's so old, it's questionable.
Okay, it looks like Curtis has joined us.
Okay. Everybody,
Curtis,
can you hear me? I finally was able to get the login information. I forgot about that. I got so many Zoom meetings going on with work and all that kind of stuff. It's getting to be a real challenge, put it that way.
Yeah.
Okay, I would like to call this meeting to order. This is the July 2021 LA Astronomical Society General Meeting for July 2021 is officially called to order at 8:05 p.m. Okay, the first thing.
Cool.
Okay, first thing on the agenda. I see we got 39 people on the thing now, on the roster right now. It's pretty good. We got pretty good turnout. Okay, first thing, this meeting is going to be recorded on YouTube. And the other thing is, second item, if you want to ask any questions or comments to the speaker, please use the chat feature on the Zoom. And of course, everybody will be muted when the speaker starts. Please post any questions in the chat or wait until after the presentation before asking questions or making comments. Okay, and we do have to fill out any door prize information. Spencer will put the link to get the door prizes so you can register for the door prizes at the end of the meeting.
Yeah, I just posted it in the chat. And my apologies.
Okay.
The next agenda item should not be there. So.
Oh, you're talking about honorary life member?
Sorry about that.
I agree. I was wondering if we had somebody that was qualified, unless of course you want to honor in this, of course you'll nominate yourself, but we didn't do it in the board, so we can't do it. Okay.
What's left over from last?
Yeah.
Huh? Yeah, I know.
What's left over from before?
Okay. For starters, I will ask, do we have any new members on here?
Yep.
Yep.
Yes.
Dave and Stefan. Both
Hi.
members.
Right here.
Tell us about yourself and why you joined or any other pertinent information.
Dave first?
Me first?
Yeah, sure.
You first.
Sure.
Okay.
Yeah, Dave, go ahead.
Sure. Hi, everybody. I guess I was going crazy over all the pandemic, and I've always had a huge interest in astronomy and astrophysics, although my life took a different course. And anyway, I went nuts and went out and bought a Dobsonian, and now I want to learn how to use it. You know, so
Yep.
yeah.
So he's going to head to Garvey.
What's that?
So you're going to head over to Garvey Ranch.
That's what I hear. That's what I
On
hear.
Wednesday nights. When we get
Wednesday
going, we'll probably get Garvey Ranch open probably the first, sometime
21st.
in August.
That's great. Yeah, that'd be great. It'd be
There
fun.
probably will be telescopes on the lawn on the 21st of this month as well.
Yes.
Okay. Yeah.
And Stefan, you're a new member, yes?
I am a new member. I'm a German transplant. I moved from Germany over to Los Angeles about 5 years ago. And it was a little bit upsetting to come here and start living under the light bulb. So I've been doing astronomy actively since 2008, I think, 2004. I got a Meade, I got an LX, I got a little portable Dobson, and I love doing it. And yeah, I got myself back into more the background of things and started studying and stuff just for myself, just for fun. So I thought like, hey, let's get back to LAS. And
that hook went in
meet
deep,
more
huh?
people.
Aaron is a new member. Hi, Aaron. This is Daryl.
This is Arun, and I have been interested in astronomy for about doing astronomy actively on and off since 2010. And I moved to Los Angeles and I moved to Pasadena in January this year. And I thought I'd try and get active in the community. Yeah, it's. I took my telescope out on tube a couple of times. There's still a lot of light pollution. I was told that Mount Pinos is a good spot, but I'm still looking for dark sky spots, and I was hoping that I could learn more about them by joining the LAAS.
And we have a dark site, so you'll be looking on the website for that information as well.
Great, thank you.
Anybody else is new? I see those three, but
Right here.
Hi,
I'm sorry,
can folks hear me? Reggie Wilkins?
barely.
Yeah.
Oh, shoot. I just paid the dues tonight. I know. So I got the email. I know a few of you folks. I'm in the Sidewalk Astronomers.
Okay.
I've
yeah,
seen you before. Yep.
Yeah, I think you've seen me.
Yeah,
What, the video's not working?
Before, Reggie.
Yeah.
Huh?
We can see you.
Yeah, you
Yeah.
can see me? Okay.
Yeah.
Yeah.
Okay, so yeah, I tried to go through my work computer, but they don't seem to like Zoom. So I went through my tablet.
Yeah.
But yeah, I know Warren, of course, and Warren is speaking tonight. So he told me, I said, I've been meaning to join for like about 5 years now, and now it's a perfect time to join because I can hear the latest from Warren on the update. Of course, I know Michael. I know a lot of you guys and gals, so I'm glad to contribute. I've been to Garvey, the observatory once a few years ago, and I really enjoyed that because it's close to Rosemead where I work, and so I'd like to go there again. But yeah, I love astronomy, of course, as many of you know, and waiting for my Paramount to get back from repairs, which is a little annoying. But I bought myself a. I
see all the laughing, nodding heads about the stuff coming back from repair. It's funny.
Yeah, I know, goodness. But I don't want to take up too much time. But I'd be honored if you guys accept me as a member. I promise to behave better than I do at the office.
All right, very cool.
David.
Okay, do we have any other new members?
Oh, yeah, right here.
Right here. Can you guys hear me?
Mike.
Mike,
Hi, I'm Mike
David.
Morris, and it's nice to be here. It's nice to join you guys, and I'm born and raised in Los Angeles. Can't seem to escape, and so here I am. Actually, I live in Ontario now, and I'm kind of new to astronomy, and I have a Skywatcher mount, and I'm in the process of buying a refractor AT-102 telescope for it. Kind of have to wait for that right now, but I just want to hang around guys with or gals with similar interest and get to know more about astronomy.
Another candidate for Garvey Ranch. Look it up on the website, see where it is. It's starting up.
Yeah.
Probably the first
Right.
event we're going to have there is the 21st of this month. And it'll be
Very good.
partially open. And then probably the following month, we might have everything done. It'll be fully open on Wednesdays.
Nice.
Yeah, and the other thing about it, if Mike is in Ontario, he could come to Ford Observatory without not too much of an effort.
Okay.
Yeah, that'd be
Yeah.
nice.
He's
Absolutely.
closer to Ford.
Hey, Daryl, be sure
Way
to
on the
bring
east
by
side.
Steve, but he's been trying to get your attention here.
Yeah, we
And
got
who
one
has-
more, David.
Can you guys hear me?
Yes.
Yes.
Yep.
Yes, we got you
Okay.
now.
So I'm new as well. Similar
Welcome.
to our first new member. I picked up the hobby at the beginning of COVID, and now I'm 2 telescopes deep in the hobby. So
Boy, that
I hope
happens
you're not
fast.
broke.
That never happened.
Only 2.
only 2. I'm looking at a third one.
I'm just a little surprised you were able to get 2 telescopes delivered during COVID.
COVID, yeah. Oh, yeah.
Everyone was out of
difficult.
stock of everything.
Yep.
Okay, are there any other new members that we can see on the roster? Any other new members?
Cool. That was a nice new bunch. Welcome, everybody.
It doesn't look like we got any new members. Welcome to all of the new members. Do appreciate that. Now, other announcements like Daryl has mentioned and I have mentioned, Garvey Ranch, we will be working on getting that officially open to the public in early August, as soon as we take care of some of logistics and cleaning up and doing some maintenance on the facilities and everything like that. So we will be getting that one open probably in early August. The last I heard, I was talking to David Zenteos on top of Mount Wilson, and he would like to try to get the public star parties in operation up at Mount Wilson. I told him we'd probably want to try to schedule something in for August as well as that. We still are still in talks on that particular issue. So at least those are the 2 main issues. Talking to Griffith Observatory I don't know if I want to mention that. I don't know if I want to mention something that they are unofficially open, but they are open on weekends only. And we're going to be trying to come up with a schedule to have the the Griffith Observatory public star parties also. So we're in process of working on a lot of our outreach and public events. As Daryl has mentioned, Garvey Ranch will be open. We're soliciting for telescopes for July 21st because we do have a scouting outreach merit badge class that particular evening. So that's what we have on the docket right now. Ford, we may be open on July 31st. We're not sure at this time. We'll have to look at the schedule and see what the moon looks like, but we were thinking on July 31st, we may open Ford up again for club members. Okay, now, do we have any other announcements to make?
I can let everyone know about 60-inch nights. We still have openings for September, October, and November.
Okay, thank you, Daryl.
August is full.
Okay. Okay, now we'll go ahead and talk to the Lockwood committee reports. You have anything to report right now?
Nothing new this month, Curtis.
Okay, that's fine. Any work programs or anything like that that you're doing that you need to get done or anything like that, or you need to call for work programs or anything?
Well, we have quite a bit of work to do, but we haven't scheduled that yet. We need to have a committee meeting first, and so we'll try to do that fairly soon. We want to, same thing as with Garvey, we need to do some cleanup in the trailer before we open that up to the public. Disinfect.
Yes.
And then there's a whole list of things we'd like to do at Lockwood that as we get funds available and time to work on it, but we just need to have a committee meeting and get it organized.
Okay, thank you, John. Appreciate that.
Curtis,
Okay.
I forgot to mention, I put my email address for Mount Wilson information in the chat. So if you're interested, email me there. Okay, sorry.
Okay, I will, scouting committee, do we have Greg on the horn tonight? Greg Thompson? Does not sound like he is on the horn tonight. We do have, like we mentioned, we do have July 21st, Wednesday night. We do have a scouting outreach merit badge class at Garvey Ranch. That is our plan right now. I have requested the City of Monterey Park that we will be using the facility on that night for in-person classes and the solicitation for the club members. We will send out a solicitation for members to bring their telescopes out to set them up on the lawn, because the refractor at Garvey Ranch will not be available. We need to do a full cleanup on that refractor. We need to work on make sure that the tracking mechanism is all up and going on it. So we will not have that available until first part of August. Okay, Ford committee, would you like to make a comment, Joe?
Well, we were out at, we had a booth at Mountaineering Days. Yeah, you can hear me. So we had a booth set up for Saturday and Sunday at Mountaineering Days, and we have some potential new members. We'll see what happens. We invited some of the town people that were interested up to a Ford Observatory. We had about 25 people show up. So it actually turned out really well, other than the 80% humidity.
Yeah, hot and humid. It's not easy up there. Okay, any other committees that we need to discuss right now?
Well, we had our dome at Garvey Ranch maintained today by C West. So we finally got some maintenance done on it.
Good.
Thank you, Joe, on that. Yes, I forgot to mention that. We did, C West came out today to do the maintenance on the Garvey Ranch dome. It would have been nice if we would have had one of our LAAS reps over there, but it didn't happen, but that's okay. I think they got the job done. I'm assuming C West does very good job of being able to protect telescopes. I don't think we had an issue with those guys. Okay, any other comments or questions before we get to the speakers? Okay, I think it's time to go to the speaker. It is Dr. Warren Skidmore. The name is familiar. I think we have had a talk from him before. I think he's going to give an update. Spencer, I will turn this over to you, okay?
Well, so I'm showing the title of the talk, which is Overview of the 30-meter telescope project. And so Dr. Skidmore will present an overview of the 30-meter telescope project, describing some of the scientific innovations for constructing the observatory, how the TMT will provide new capabilities to push the frontiers of astronomical research, technical solutions and design of the telescope, optics and instruments, status of construction, and the project's participation in the U.S. extremely large telescope program. So Dr. Skidmore is the TMT instrument system scientist and has been part of the project since 2002. And his role is to ensure that the TMT observatory will provide the observational and operational capabilities needed to conduct cutting-edge research science and have the abilities to address the diverse range of astronomical questions that research astronomers develop. So I'm going to turn over to Dr. Skidmore. So I'm going to stop sharing the screen and you can take control.
Super. Thanks very much. Can you hear me okay?
Yeah.
So far, so good.
Good, good. So I'll just try and share my screen. And I'm sharing my PowerPoint. Let me put it into... so you can see the presenter view, right?
Yes, we see the slides at the bottom as well.
Yeah, we're seeing your view.
So that's the proper.
There we go.
Now.
There we go.
So I'm really pleased. Thanks, Tim, for reaching out recently. So it's good to see some familiar faces, and you know, I gave a talk in person about 5 years ago or something. You know, actually at Griffith Observatory. So it's great to be able to touch base with you guys and give you part two, or you know, an update on the project since then. And you know, yeah, I'll get on because I've got too many slides for the time, I'm afraid. So I will speak quite quickly. And if at the moment I can't see the chat, so if someone in authority could monitor the chat and if necessary interrupt, I'm happy to do that. But otherwise, we'll have to you know, work together at the end, like described. Okay, so 30-meter telescope. You know, I've been working on this project for a long time, and you know, our aim is to build a general-purpose observatory, something that, in many ways, it looks very traditional. You know, big mirror, primary, secondary, tertiary configuration, Ritchie-Chrétien for those that know about optics, and the tertiary mirror. Can you see my cursor okay if I use it as a pointer? Okay, I see nods.
Yes.
So
Yes, we can see it.
tertiary mirror can steer the beam to different instruments. And so it's a general purpose observatory that we're trying to build that can support a range of different sorts of instruments and do a lot of different sort of science. So this is a parameter space plot. You know, the spectral resolution, you know, how much we're dispersing the light into its colors, the spatial resolution, the detail that we can see on the sky, and the boxes represent the capabilities of different instruments. The green ones are ones we're building right now, and the yellow and red ones are ones which are destined for, they're in the pipeline for future instrument development. And we've chosen these types of instruments and their capabilities so that we can do all kinds of different sorts of science. And really, the new telescope that we're trying to build, it gives us two new capabilities that I'll talk more about in a bit. And one is spatial resolution. So a lot of the science we want to do, you need to see very, very fine detail, finer than you can see with the 8 and 10 meter class telescopes that we have today. I'm sure all of you know about diffraction and that kind of thing. So the wavelength divided by the diameter of the telescope tells you the finest spatial scale that you could possibly achieve. And of course, we have to use adaptive optics. I'll talk about that later in order to do that. And then a big light bucket as well to get more sensitivity. The spatial resolution and big light bucket actually gives a very, it's a powerful multiplier in terms of sensitivity. So, we're many times more sensitive than the 8 and 10 meter class telescopes that we have today. Let's see. Trying to go to the next slide. So, we're trying to build a general purpose telescope, but it's a very complex system. The whole observatory, lots of different instruments, the telescope optics. You'll see more details. Some of you may be relatively familiar with all of this stuff, but I'll cover it all. The whole machine, the structure and control system of the telescope itself, the enclosure. It's a really complex system, but it's just a general purpose observatory, just a really big one. So the next slide. And we have this international partnership that's formed in order to build the observatory. It started with Canada and Canada and California and the United States program. Originally, they all merged and formed the TMT project, and that was back in 2004. And I'm sure most of you have heard about that we've tried to start construction and there were protests, and we've tried to start again and there were more protests. So we're in this sort of phase at the moment where at the moment we're trying to re-baseline the project, replan, and get ready to start construction somewhere at some point soon. Our primary site is Hawaii, but we have an alternate site in the Canary Islands, in La Palma. The two sites they're both excellent sites, but they are different. Hawaii has slightly better scientific capabilities, as it were. The conditions are it's a higher altitude site. The conditions are a little bit better. The conditions in the Canary Islands are excellent. We can do all of the core science that we want to do with TMT. We just got to build the thing and get going. So even though we're not digging holes in the ground, a lot of project work is continuing, and I'll tell you something about that as we go through the talk. And so construction activities are not limited to work on the summit. There's a lot of work going on. There are two other projects in construction at the moment: the European Extremely Large Telescope, 39 meter diameter, and the Giant Magellan Telescope, whose offices are here in Pasadena. And both those projects are moving forward. And I'll tell you a bit about the Giant Magellan Telescope, or our partnership with it right now, in fact. So the US as a nation is not formally involved in an extremely large telescope project. So a few years ago, the US Extremely Large Telescope program was launched, and this, TMT has been starting the process of seeking federal funding. The Giant Magellan Telescope, they're in a similar situation. They need federal funding also to complete their project. But what is happening is this body, NOAA Lab, people would know it previously as NOAO, National Optical Astronomical Observatories. It's been rebranded, reformed, and it's now called NOAA Lab. But the NOAA Lab is developing this program, and TMT and the Giant Magellan Telescope, we're both really participating closely and working together and defining this program where US astronomers will have access to both telescopes in some sort of combined, you can send one proposal and you could propose for time on both telescopes. Each telescope or each observatory will be operated independently, but they'll be operated at least part of the time through this umbrella, through Noir Lab and this program. So this is a way for US astronomers to actually get time on these telescopes. So that's very exciting. I'll skim over quickly. So, the two sites, we have all the legal authority to build in either site. Here's some little simulations of what TMT would look like in Hawaii and what TMT would look like if it was built on La Palma. They're both volcanoes in the middle of the ocean, both excellent sites, but we are not yet in a position where we can move forward. So something that is important is this situation that we're in Hawaii. I'm an astronomer, I'm a scientist, I'm not an expert in this topic. I can't speak authoritatively about it at all, but I work on a project which is, the intent is to construct a telescope on a site, on a mountain, which is very special to many people. So, I'm directly affected by it, but I can't speak well on the situation, but I do want to acknowledge it because there are real concerns, and it's part of a long set of long-term problems that the native people in Hawaii are having to deal with. There's a lot of history, and they haven't had a good time in the past, and a lot of them don't have a good time right now. They're still trying to come out of this situation that they found themselves in the past. TMT is trying to find ways to move forward, but it's a very difficult problem. It's a very high-profile project for sure, and is why it's attracted so much attention. But it's only one issue that the native people in Hawaii are dealing with. So I can't speak much more about it than that, apart from to acknowledge that we are entwined with this in this problem, and people actually on a higher pay grade than me are working on how to move forward with this. But I can talk about technology and particularly about the science. So I know a lot of you guys are interested in tangible stuff. So I'm going to tell you about the design and state of readiness of the project. So that there's a big enclosure that's going to cover the telescope that's going to be made in Canada. That's at a point where they're making production drawings. They're just sort of waiting now until we're ready to kick off full construction. But everything is ready to start production, fabrication of the enclosure. There's been a lot of prototyping work and testing, and this sort of thing is kind of cool to see. The bogies that the thing runs on, and test them to, well, they never got destroyed, so they certainly look like they lasted for the full 50-year lifetime of the observatory. And the control systems, this sort of stuff, the software, this is something you can work on quite easily, and there's certainly a lot of software work being done across the whole observatory. These are the big the prototype of one of the big shutters that goes around the enclosure to let the airflow through the enclosure. Similarly for the telescope structure, there's a lot of prototyping work, no real fabrication, but they've got production drawings, they're ready to go. And I've got a couple of pictures here from a safety review, evacuating and how you manage all, this picture of the moving the bottles around on the telescopes. Part of this, it has to be a safe process. So it's not just evacuation and things like that. It's looking end to end at all the maintenance processes and that kind of thing. All of that has been worked out. And, you know, we even know where all the light switches have to go on the telescope. It's pretty amazing. Some of you may remember this image from years ago. I use it all the time because the most technically challenging part of the whole telescope was building this mirror, and you know, technically very risky, but a huge amount of development work was done, and we're building it. We're making the mirror as we speak, and I'll show you some pictures. But just to remind you, what a 30-meter mirror, how big it is. You know, a baseball diamond or a basketball court. It's just absolutely immense, 30 meters across, and controlled to nanometer levels. So this is up at Coherent, a company north of here, I think in the San Francisco area. I'm not an engineer, so I don't get to go to these places. I get to meet the scientists that want to use the telescope. But there's all this cool stuff that's been made over in Monrovia, just a few miles from here. This is a picture of it's upside down. This is one of the support structures from behind one of the segments. We've got, this is real stuff that's going to go in the telescope. That picture up on the upper left. This upper right is a prototype, and lower right as well, developing the process, testing segments after they've been polished. That process has been developed, and this is actually manufacturing all this support structure that goes behind the segments. That's in full swing. We're making this stuff.
Excuse me, Warren. There are a couple of questions that came up in the chat. Do you want to take them now, or do you want to wait?
It depends what they are.
Okay, so one of them is there's one about why are hexagonal segments used in designing the telescope? Does it have to do with packing efficiency?
It was a number of factors. Packing efficiency is one, but it's mainly producibility, or ability to make them, and control them, and also technical risk. We already have the Keck telescopes and a few other segmented mirror telescopes, and they all use hexagonal segments. It's easier to make a hexagonal segment than it is a square segment, for example. And there's also more edges on a hexagonal segment. So you have sensors on each edge, so you can measure the position of one segment with respect to its neighbor. So you have more measurements to control, to feed into the control loop. So it's mainly manufacturability and control. Right? I would answer it that way. What was the other question?
The other one is where do the funds come from? I think you kind of answered that. How many years will it take to build?
So at the moment in the US, we are privately funded from Caltech, University of California, and the Moore Foundation. And federal funds are coming from Canada, China, India, and Japan. And we're seeking additional federal funding as well. And if we would start to build the thing tomorrow, it would take about 10 years before we could say, okay, it's ready. Let's start. Well, before we could show, we expect that we'd be doing a significant amount of science with it. Take about 10 years to build. Is that okay? Should I move on?
Sure. Yeah. Thanks.
Super. So we're building lots of this hardware. All the stuff that's been goes at the back of the mirrors is being built over in India. There's a few sites over there where that's been done. Telescope optics, these segments. First, you pour a blank, and they're all being made in Japan, every single one of them. But they're being shipped to to the US, to China, and India, and they're keeping some in Japan to process, to polish, and turn into hexagonal segments. And we've got more. These numbers are actually out of date. I think we have all the blanks for the telescope now. I might be wrong because things slow down a bit because of COVID, but these numbers are definitely out of date now. I think we have about 130, something like that, in California now. And but they're not just being stored; they're actually being processed. So these are test maps of polished segments up at the Coherent factory. I'll go through quickly. There's polishing in the US. This middle picture is in China. They've developed their own polishing process because it's a restricted technology. So we've defined requirements that they have to meet. How they do that, it's up to them. But they have to deliver polished segments of the right quality, and they can do it. They've demonstrated that. This facility on the right is in India, just outside Bangalore. So that's a whole new facility built just for polishing TMT segments over there. A lot of investment from the partners. Test optics. There's so much. This is polished segments up in California being inspected, and it's really moving forward. You see all these segments here on the left, and that's only a few. There's stacks of them, absolutely loads. This is test equipment. This has to go on the top of a 5-story tower to look down and look at the segment of the segments to make sure they meet the right requirements. And this is the Coherent team, just to show you there's lots of people involved in building TMT. Some of you on this meeting, I know, have visited our facility in Monrovia, so you'll have seen this. Some of these slides will be things which are familiar to you. These are more of these segment support assemblies. These are going to go in the telescope eventually. Testing stuff. So much testing going on. These gold blocks, they're made of glass coated in gold. They're the capacitive edge sensors. There's 12 of them around each segment. One block goes on one side, one on the other, and it's a capacitor basically. And if you move the capacitor in piston up and down, or in tilt, in angle, it changes the capacitance. You can see JPL they're on this circuit board. They're developing that system for us. And they get covered with these dust boots, which I thoroughly tested in this picture. That's dustier than you'd ever get in an observatory, I'm sure. So it looks good. So and this is our multi-segment test bed, which I know some of you have seen in Monrovia. And we should keep in touch because as things open up post-COVID, it might be good to organise an LAAS trip to our lab, because that would be a bit of a fun thing to do. So just looking back at this, just to remind you, we're trying to build a general purpose telescope that can support lots of different instruments and has these two new capabilities: spatial resolution and sensitivity. So spatial resolution, it's pretty clear why you need better spatial resolution. We're looking at objects typically that are very far away, and higher spatial resolution will allow you to see much more detail in those objects. And then one example of science not so far away, actually, Io, the moon of Jupiter, has eruptions on it, and these lower left figures from the original images were taken with the spacecraft, but they were passed through this simulation system. IRIS is one of the instruments we're building. So this is a simulation of what we expect one of the first light instruments for TMT would do. And you can see on the lower right picture here, this ejector from a volcano that's landed on the surface of Io. So we can look at these kind of details in our solar system. Sensitivity is huge. So this is a picture of a campfire. And if we have a bigger light bucket, then obviously you'll collect more light. But when you combine it with the spatial resolution, you know, it really enhances the sensitivity of the system. And that's very powerful when it comes to science. So on the left, this is some field in Andromeda. And this is what we can do at the moment on the left. And this is a simulation of what we should be able to do with TMT on the right. On the left, you can see the brightest stars. On the right, you can see a huge number. You can see very faint stars. Make them out all separately. So what this allows us to do is, this is, I'll talk a little bit longer. This is the core of Andromeda. So you can see, you can make out this on the left is with Hubble Space Telescope. On the right is a simulation that we would get with TMT. So you can see all these faint individual stars that we can see in galaxies outside of the Milky Way. So I'm talking about Andromeda here, but that applies to all the local group of galaxies. And there's 150 or a couple of hundred galaxies even in the local group if you include dwarf galaxies. So what that allows us to do, Hertzsprung-Russell diagrams, look at the main sequence, studying the stellar populations in different environments. How does the environment affect the masses of the stars that grow? The distribution of the masses. How are elements incorporated into stars? All that kind of stuff. We can do a lot more research, even in our even in the Milky Way. At the moment, if you look at a star cluster, you can't see the faintest stars in the star cluster, even with the big telescopes. You can only see the bright ones. But with TMT, we'll be able to see all hydrogen burning stars in a whole bunch of clusters around the solar neighborhood. So it'll really allow us to look at because the smaller stars are the most common ones. So it'll really allow us to learn a lot about star formation and stellar populations in general. So I'm sure all of you on this call know about spectroscopy. Telescope collects light from some object you're looking at. You disperse the light into its constituent colors, and you can that's a very powerful way of looking at the physical, chemical properties of whatever you're looking at. Every element has a unique spectral fingerprint, so we can look at the chemistry, but we can also look at the temperature, the density, the pressure, the velocity of objects. And here's an example of looking at a star that wobbles because there's a planet going around it. We see absorption lines in the spectra of stars moving backwards and forwards in velocity, and you can infer information about the mass of the object that's orbiting around it. And in many cases, they can be binary stars, but sometimes they're exoplanets. So spectroscopy is a powerful tool that astronomers use. Oops. Let me restart my. Of course, that would happen, wouldn't it, in the middle of a presentation? So yeah, spectroscopy. You can't see my screen at the moment, or you can't see what I want you to be looking at. Let me see if this will work. I'm just. One thing we'll be able to do with TMT is we're building something called an integral field spectrograph. And it's not there. So we can do spatially resolved spectroscopy. So for every pixel that you would have in an image, we can take a full spectrum. Are you seeing my screen? Can anyone confirm?
No, I'm not.
Still seeing.
We're not seeing a screen at all.
All right, I may need to share again then. I'll do that in a second. Yeah, I've started the presentation again. So you're seeing it now, I'm sure.
Yes.
Yes.
Super. So spatially resolved spectroscopy, instead of just getting a single pixel, as it were, dispersing the light, we can make these 3D cubes of X and Y spatial dimensions and wavelength in these cubes. So these are super powerful tools. If you're looking at I know a galaxy, I'll talk about those in a bit, or some cloud of gas where something interesting is happening, you can probe what's going on inside the object you're looking at using these types of instruments. So I've started to head towards the scientific motivations for building this huge telescope. How am I for time, by the way? Because I do talk a lot.
You're fine.
Okay. I've only got 55 slides left. And the scientific motivations, at least in my opinion, as an astronomer, are huge. This image here represents the history of the universe. On the left-hand side, from the Big Bang, these cosmic dark ages when nothing was, the universe had cooled, become transparent, but no stars and galaxies had formed. And then, the first galaxies start to form, big stars start exploding, enriching the universe chemically, and reionizing the universe, and that process continues, and there's more and more chemical enrichment until we end up in a state like the present day, where there's a lot of chemistry in the universe, and a lot of interesting processes going on. So, with something like TMT, we will be able to probe the full history of the universe, and I'll show you why in a bit, which we can't do at the moment. We don't have telescopes big enough to do it. But for TMT, once we get that, we'll be able to do it. So there's lots of questions about the way stars form in different environments. I mentioned that, in the early universe, when there was only hydrogen and helium, that process of formation is different to when there's lots of other chemical elements. This is a simulation of if you look at the middle screen, the red stuff is hot gas and the green stuff is cold gas, and it's all falling down due to gravity, forming galaxies in the center of this simulation. So each blob is a galaxy with hundreds and thousands, perhaps millions, even billions of stars in some cases. But so on the left is what you would see optically. The gas isn't glowing, especially the cool gas. You can't see it. But the simulations on the right are showing how that gas moves and how it feeds the growth of galaxies. But we want to study this process. And at the moment, I think on the next slide I can show better. If you have a quasar, the light from that quasar passes through the filaments of material which pervade the universe. And those filaments of material imprint absorption lines on the spectrum. So you can look at a quasar, which is effectively a hot black body source, look at the absorption lines at different wavelengths. And because the universe is expanding, different regions are moving away at different velocities. Each wavelength corresponds to a distance from us. We can map the structure of the universe, but we're limited by the number of quasars that are out there at the moment. Quasars they're giant black holes. There's not many of them in the early universe, that's for sure. It takes time for these big black holes to form. There's not that many quasars, but there are a lot of small galaxies. And this region, this time period, reionization, we really want to try and study what the universe was like in that time. And something like TMT, with its high sensitivity, we'll be able to use the first galaxies that formed, early galaxies, as these sources behind all of the intervening material. And we'll be able to map the universe on a much higher spatial density and to a much more distant age as well, earlier age than we can at the moment. That'll be very exciting. And this is an instrument that's been built for it. It's officially in its conceptual design phase at the moment. Look at the size of this instrument. There's a standard SolidWorks guy standing next to it. This is one instrument. It's huge, you know, and it's going to be, you know, there's not going to be much change from $100 million to build this instrument. And the light from the telescope comes in from the left-hand side into this nose, as it were, and then down into this multi-object spectrograph. And that will allow, you know, we can measure the spectra of a bunch of different objects all in one go with that. So that's looking at the cosmic web, the gas that pervades the universe. But looking at the galaxies themselves, you know, the telescope at Palomar couldn't reach particularly high redshift compared to what we want, compared to the entire age of the universe. The 10-meter telescopes can't reach too far, but with something like TMT, we'll be able to observe every galaxy that has ever existed. It's a quantum leap in our capabilities. Every galaxy that's ever existed is within reach of TMT. Not individual stars, but the first galaxies that ever formed. We can study them. So that's really exciting. And here's a simulation. I'll skip through it, but it shows, you know, the Milky Way is formed from lots of small galaxies that coalesced. And there are small galaxies still around us that haven't been subsumed into bigger galaxies. But we want to study those galaxies in primordial times, when the universe was completely different to what it is around us now. To do that, we need to get to the diffraction limit. This video on the right is of Betelgeuse. This 4.2 meter William Herschel telescope is in La Palma, and this is like a high magnification image of Betelgeuse. It shows the way that the atmosphere breaks up the image, and you know, we have to use deformable mirrors and measure that pattern on the right hand side. Use deformable mirrors to apply a correction and sharpen the images so that we get the true image before it's been spoiled by the Earth's atmosphere. So we're developing a system for TMT, an adaptive optics system, and it's as big as it's about as big as my house, at least in Altadena. It's you know, it's as big as a small house. The adaptive optics system. 2 mirrors. Mirrors have been made over in France. The wavefront sensors, all this technology is being developed around the world, actually, for TMT. Let's see, and you know, this is the facility that was built in the last couple of years up in Canada. There's a simulation of the adaptive optics system. It's called Nefarious, the adaptive optics system, inside it. But this building is built so that the adaptive optics system can be integrated and tested up there. And this is a first piece of that process, a cooling system delivered from China. So this is a cryogenic system that cools not the enclosure, but components of the adaptive optics system. And that will go, well, that's already in that building up in Canada, ready to start this process. The laser guide star system is in final design. So you know, we want to point the telescope anywhere in space, anywhere in the sky. There isn't always a bright star nearby to use for adaptive optics. So we make our own guide stars by shining a laser up into the atmosphere, and that system is well designed and mature, and all that is to get images or to deliver diffraction limited high spatial resolution images in the focal plane of the telescope, and we can look at these galaxies, the first galaxies that ever formed, and they're about like an arc second across, something like that, and we can look spatially across them and look at the distribution of chemical elements, the velocity of the stars and gas in some cases, and really start to understand how those galaxies are forming in the early universe. And we just, we don't have that ability today. So the instrument we're building for that is this thing called IRIS. The bottom part is being built over at UCLA, the green stuff. The orange kind of tan stuff in the middle, that's the an imager that's been built over in Japan. The bottom part is this integral field spectrograph. That's the thing that's been built at UCLA. They've built a couple of those in the past and do a very good job. So we're trying to skip over as quickly as possible. Yeah, lots of people involved in that, and they're building bits, and a lot of prototyping work still at the moment, but some first articles are being built. Something cool that this IRIS instrument will do, you've heard of gravitational lensing. This is, not only can we just inherently see these galaxies that were started, formed in the early universe, by looking at something that's gravitationally lensed. It's like a zoom lens to see what these galaxies look like. So all these these galaxies which are stretched into a ring, they're actually magnified to some degree, quite a lot in some cases. But you can see they're distorted by the lens itself. So there's you have to understand the lens that's causing this. But if you understand the lens, you can kind of deconvolve what these galaxies look like and see the details in those galaxies. So this is a simulation. This is a it's real data on the left from ALMA of a lensed galaxy. So this is probably the core of the galaxy, and then the spiral arms or something. I'm just speculating there, but the point is, there's the structure of the galaxy is magnified, and at the moment, the middle image shows the sort of detail of the arcs that we can see with the Keck telescopes, and the extra detail we'll be able to see with TMT. So it'll really allow us to, in special circumstances, of which there are many around the sky, really look at what's going on inside these early galaxies. It's very exciting. Exoplanets is a huge motivator for TMT, trying to we've found thousands of exoplanets, but we've characterized very, very few, and characterization is where we answer the big questions like, is there life on the exoplanet? And to do that, you need to be able to look at the constituents of the atmosphere and see if the atmosphere is in chemical equilibrium, in which case there's probably no life. If it's out of chemical equilibrium, like it is on Earth, that could be evidence of life. And then, the astrobiologists have to think about exactly, what the constituents of the atmosphere are, what could drive it out of chemical equilibrium, that kind of thing. So we're building, this is at Caltech, they're building this instrument called MODIS. They've already built a couple of these spectrographs, one's at Palomar, one's over at Keck, and this system for injecting the light into an optical fiber from the adaptive optics system. They're building, they've built one at Keck, and they're refining it at the moment, but they're building the same sort of system for TMT, and this will give us the ability to study the atmospheres of exoplanets. I'm getting towards the end now, but I think this is the last slide about science. Transient science, things that explode and that you need to the whole observatory to respond quickly to, you know, something's happened over here, you know, turn the telescope and reconfigure the instruments to whatever types of observations you want to take. The whole observatory is designed to react quickly. And by quickly, I mean finish one observation and start observing on another one in less than 10 minutes, from end to end, which includes changing the instrument, getting on target, acquiring adaptive optics guide stars, setting up the adaptive optics system, and getting ready to start observations in 10 minutes so you can start taking data. And you know, this is a telescope that weighs as much as a small ship, so it's you know, moving at that kind of speed is pretty impressive. You know, even smaller telescopes have difficulty doing that these days. But you know, the design this system for TMT, which, as far as we can tell, it should do it. And I'm part of the commissioning team, so I've got to make sure it does do it when we finally build it. So this is my last official slide. It's just a little movie that I like to leave people with, because it's, you know, we're building this amazing telescope. It's going to do amazing science. It's bringing countries together that in many other realms have their differences, but we're all working together to, you know, to build this amazing observatory. And it's a very exciting project to work on. So I'll stop there. I'll stop sharing, and Spencer, if you could run through the questions, that would be much appreciated.
Sure. So let's see. I'm scrolling back. There are a couple of comments. So one is, I wonder if this technology will be outdated in 10 years from now. But it looks like they'll be able to add new tech to the future, in the future, to the TMT.
So the technology is new in some respects, but it's already existing technology. You know, we have the Keck telescopes, which are 10-meter segmented mirror telescopes, and we've improved on those systems, and we are able to then build a 30-meter mirror and control that. You know, the adaptive optics system, again, it's using existing techniques, pushing the technology so the performance is better and things like that. So you know, a lot of the technology was probably going to be around in various forms for years and years. And even though in 10 years time, you know, that's the sort of time we think TMT will be running, it'll be cutting edge for sure. And there may be development programs for smaller telescopes, which there is now for extreme adaptive optics, but it's typically on smaller telescopes. And when that is matured, we'll be able to employ it on something like TMT.
So, okay, another question is, let's see, how is the TMT different from the James Webb telescope?
Extremely different. The James Webb telescope, because it's in space, is, you know, it's a cold telescope. It operates at much longer wavelengths. So TMT is designed to work in the optical, you know, say 310 nanometers, the bluest you can see with the naked eye, to 28 microns. That's our technical requirement, the longest wavelength, which is, I think that's a wavelength where, you know, if you hold your hands up, you'll feel the warmth at 28 micron. I think it's, you know, that sort of wavelength. But James Webb telescope works up, you know, hundreds of microns. So it's longer wavelengths, and it's a much smaller diameter mirror, but because it's cold and it's in space, in the mid-infrared, which is where James Webb's designed to work, it'll have higher sensitivity than the 30-meter telescope, but it won't have the spatial resolution. So in that way, they're complementary. TMT has capabilities that James Webb Space Telescope won't have, and James Webb Space Telescope is more sensitive than TMT will be. So they complement each other in that sense. But there's different sorts of instrumentation. A lot of the science goals are very similar. There's a lot of overlap in the science goals, but the way you tackle those science goals would be different. The techniques you employ.
Well, I guess one inherent advantage is that you could easily upgrade instruments on the TMT. Where
that is a huge advantage as well. You can fix things when they break. You can have much more complex instruments because if they break, you fix them. They don't need to be rated to go into space necessarily, but you do. I was showing you the IRIS instrument, and the idea is that when you cool that down inside its dewar, you don't open it for the next 10 years. So you do need very high reliability on, akin to the sort of level of reliability, they need for space.
Okay, so another question from Stefan is, when you create an artificial guide star with a laser, do you need to coordinate with air traffic control first?
The plan, not air traffic control, but Space Command has a lot to do with using laser guide stars, because they want to protect space assets. So we'll have to coordinate with them. But the system that they're trying to develop nowadays, and it has really been developed now, is you ask Space Command where you can't look, and they send a few patches of the sky back and they say you can't look there. So most of the sky is open most of the time, and that's the sort of situation that we want to have. The plan is to run TMT using an adaptive schedule, so that we, if the seeing is bad, if the conditions are bad, we pick certain science programs. If the conditions are good, we pick other ones. If we can't observe over there in the sky, we leave this science program till later because we can observe in that part of the sky and project delay. So we'll do this program, and we match the programs with the conditions and the abilities to make observations. So there are aircraft safety systems on it. I forget all the acronyms. It's not. But my understanding is that every aircraft's supposed to have some kind of transponder on it. So there are these little, some little like phased array things that can tell where the aircraft are, and that they'll shut down if the aircraft is going to come, in the line of sight. So there's an automatic safety system for that. But Space Command is the thing that I think about the most, because you're not allowed to fly aeroplanes over La Palma, and Mauna Kea is already 13,500 feet high, so there's not many planes anywhere near the top of that normally.
How strong is that laser? It seems like if Space Command's worried about it, it must be pretty powerful.
So I think the plan for us, we're going to have 10. I think they're 20-watt lasers. You have to figure. I'll be correct to within a factor 2. I can guarantee that. So they're either 20 or 50-watt lasers. Well, that's within a factor 3. Either 20 or 50-watt lasers, and I think 8 of them work at the same time, but we project 6 laser spots. So all the light from those lasers. So each laser beam is like 50 watts or something, about that, and there's about 6 beams. They're a fairly tight you know, like if you're standing under the telescope, it look like a single beam going up, but you know, they're launched from just behind the secondary mirror. So they're dangerous. There's a lot of safety related to them. That's for sure.
Okay, so another question is, how does the dome close the opening?
Let me see if I just share my screen again.
Sure.
That movie I just finished with. Let's see if I can play that. So I'll try and play this again. Now watch, just as we fly, you'll see there's a big cap that's rotating out. Do you see it? Hopefully, I'll show it again. It starts about here, doesn't it? So there's this cap that rotates on a frame inside the dome, and that plugs up the hole. It used to be called I think it is called a plug. The cap is the thing that was on about a 30-degree angle. So there's this plug that rotates around on a frame inside the enclosure, and around the plug there are flaps as well, which come down to seal it and open up to direct the air, the wind away from the top end of the telescope. You can see the flaps here quite nicely.
A couple more questions. What's the latency like when using adaptive optics, and are all the steps between detection and physical, and what are the steps between detection and physical adjustment of the mirrors?
So let's answer the first one for latency with adaptive optics. So when you slew the telescope, you always have to acquire the target, or acquire typically, you know, some guide stars, and then adjust the pointing of the telescope so that you're right on the target. When you're using adaptive optics, there's an additional step where you have to turn the adaptive optics system on, measure the wavefronts, measure that pattern of disturbance, and start the adaptive optics, the deformable mirror actuation system. So for the adaptive optics system, from the time we've slewed the telescope and acquired the guide stars, we have to be able to lock the adaptive optics system in 2 minutes in the multi-conjugate adaptive optics laser guide star mode. So that's like the most complicated mode. And as far as I know, the simulations of this process, it should occur much quicker than that. Of course, you know, experience may be something different, but when they simulate the operation of the system, it looks like 30 seconds is a good time. When I've been down in Chile, there's the Gemini telescope has a multi-conjugate adaptive optics system, and they're typically, if you know, slew the telescope and you turn the laser on and you turn the adaptive optics system on, if you can do that in less than 10 minutes, you're doing really well. So we have a much higher requirement of this like 2-minute latency, this dead time, to get the adaptive optics system ready. And it looks like we should be able to achieve that with this system that's been designed and is actually being built at the moment.
So that's the time to get it going, but when it's actually in operation, how quickly will it respond to shifts in the atmosphere?
Oh, I'm sorry. Yeah, it depends how bright because you always need a natural guide star. You always need a star near where you're looking. But if you've got lasers, that guide star can be further away from your science target, and the latency depends on basically the brightness of your tip tilt star, this natural star, and it'll typically be about 800 hertz. That'll be the correction. You know, the mirror will be fluctuating, the actuators actuating at about an 800 hertz frequency, But if you've got a bright guide star, you can push that up to 1200 hertz. And I think the lowest mode is about 200 hertz, but that probably would give you a very poor correction. And but that range between 200 and 1200 hertz.
It seemed like you could almost hear it humming.
You could actually, yes, yeah, it's that frequency, yeah.
Mm-hmm. All right, let's see. So another this is dear to a lot of us. Any thoughts on how to remove any influence from Starlink satellites?
TMT is lucky in some respects because the field of view is very, very small. So if you're pointing in a certain direction, the chance of a satellite passing over is quite small. But the impact is more on the propagation of lasers, because if we're going to hit a satellite, they don't want to shoot in lasers up. So the expectation is that for TMT observations, the impact of the Starlink satellites and the other constellations which are planned as well is very small actually, but it impacts our ability to project lasers, because the patches of the sky that they say we're not allowed to project on a couple of degrees across or a few degrees across, and there might just be one satellite passing through that patch, but you can't observe in that whole patch, and of course, so if there's lots of patches where you can't observe, it'll start to impact us that way. So that's different to things like the Rubin Observatory, what was known as the Large Synoptic Survey Telescope. That's got a big wide-angle camera, and just like every image from that is going to have satellite tracks through it. So or a very high proportion. So that type of telescope, a wide-angle telescope, would be affected a lot more. But for TMT, we're looking for that diffraction limit, that high spatial resolution. Our fields of view are very small. The IRIS instrument has an imager, and it's 33 arc seconds on a side. That's like if you put a period on your finger and hold your finger at arm's length, that's the kind of field of view. A period on your finger at arm's length. It's very small fields of view, which saves us from a lot of that. But we are definitely aware of it. And there's a conference this week that I'm participating in on this very topic. Okay.
So another question. So I think I saw that the telescope field is 20 arc minutes. That seems enormous. Is there an instrument that uses the entire field?
No. Now, you're right. The focal length or the effective focal length of the telescope is 450 meters, and a 20 arc minute field of view, that equates to, I think, 2.4 meters. Where those instruments are on the Naismith platforms, you'd need a lens or something 2.4 meters across to use all of that field. And so at the moment we don't have plans for anything specific to use that. There are instruments with deployable optics. So say like a multi-object spectrograph, where you have multiple integral field units and they're on an arm, and that can, these arms are as big as a human arm, and then they can move around, and you perhaps have half a dozen or a dozen of them, and they could utilize that sort of field. But all of that is just over beer type chat at conferences and things. There's nothing concrete that uses a significant, really significant field of view yet. The one instrument we're building at first light has an 8 by 3 arc-minute field. That's WFOS, and that has lenses in it which are a meter across, huge optics. Very, very challenging and very, very expensive.
All right, there's several questions relating to the mirror vibrating, and somebody mentioned that it looks like it's a above middle A, just a little bit flat. The tone that it makes when the mirrors are deforming.
Oh yeah. You're talking about the adaptive optic.
Yeah, right. Yes. Yes.
Because when you talk about the mirrors vibrating, something I've worked on quite a lot is, we've got this 30-meter mirror, and we have to hold the segments to a few nanometers position, and this is essentially it's like an industrial facility that we're running, and there are pumps and compressors and cooling systems and all sorts of machinery in the building right next to the telescope. And a lot of that machinery could, if we make a mistake, it could inject vibrations into the structure of the through the ground into the telescope pier and into the telescope itself, and cause all the optics to vibrate, and that would definitely degrade the performance of the telescope quite a lot. If the optics are vibrating, so we're thinking about the tone of the adaptive optic system, but talking seriously, the vibrations throughout the observatory building are a very serious concern, because they could really impact the performance of the entire system.
Okay, let's see. One question was, what's the power? What will power the site?
If assuming we build it in Hawaii, there's the Hawaii Electric Light Company. They generate the power in Hawaii, and we'll tap into that power supply. The peak power that we need is when we're moving the dome, and it's on the order of a megawatt.
Wow.
And the average power, I think averaged over like a typical 24-hour cycle, is about 250 kilowatts, because we have a lot of air conditioning running during the day. That air conditioning is I think the biggest single component when you add it all up, and the highest component in terms of instantaneous power is moving the dome. But I was told a long time ago that you could fit all of the cables to power TMT in a 4-inch conduit underground. So, but it comes from the Hawaii Electric Light Company.
So you must have provisions for emergency generators and things like that to maintain.
There are, yes, yeah. If the power gets cut, we need to close down gracefully. There's no provision to continue operations in the absence of mains power, as it were. But we do need to be able to close the dome, ramp down the use of computers and things like that. So UPSs, emergency generators, that's part of the design.
Yeah, megawatt's pretty good load coming from an Edison person here. That's a big business.
Yeah,
That's
the emergency generator would only close the dome slowly. So it would be significantly less. The generators, it's all quite modest when you work it out. But instead of we're not operating if there's no power. We've got to make the system safe. We've got to be able to park the telescope so that it's as safe as possible. That sort of thing.
Okay, a couple of questions relating to conflict with local groups objecting to construction of a sacred site. And you mentioned that was discussions are taking place at a much higher grade level.
Yeah, I'm quite reluctant to speak about it because it's such a sensitive subject, and I don't know enough about it to speak confidently. But what I can say is that there's a lot being done, and of the details of which I'm unaware of. But there's a lot of efforts to try to reconciliation and trying to find a path forward. I can say things like, from years ago, I was part of the site testing group, and we were testing sites in Chile, Hawaii, Mexico, and we didn't know where we wanted to build TMT. And in Hawaii, there was always this recognition that we have to do things in a different way than previously. We have to be a good member of the community. We have to be sensitive to the needs and concerns of local people, and the plans for the construction and the operation of TMT. A lot of effort was made to agreements with local labor unions and this kind of thing, commitments to hire a certain fraction, a high fraction of people locally, and in order to be able to do that, to develop a workforce pipeline program and that kind of thing, the things that TMT could do to try to be a positive member of the community, they tried to do, but TMT can't fix all the issues that people are concerned about in Hawaii. But the organization, as it were, has tried to do the best it can to be a positive, to have a positive impact.
So last question on the chat is how many stories is it equivalent to?
Say again.
The last question I see in the chat is how many stories is it equivalent to? I guess the height of the structure.
Yeah, so you see in the news of things like an 18-story building, that kind of thing. So I'm not quite sure of the calibration. I know that the top of the dome is 55 meters high, and I think the diameter is about 60 and a bit. Yeah, but it's basically a ball with a little bit chopped off the bottom. So a 55-meter high sphere, which if you saw that figure I showed earlier of the simulation of the observatory on the mountain, if you scan back and look at the mountain as a whole, it's not a huge part of the mountain, but on a human scale, if you're standing next to the observatory, it'll really be a big structure, and it's possible to sort of tuck it away so that it's in a site where the conditions are still good, but it minimizes the visual impact. Like you can only see the site, and you'll only be able to see the telescope from, I think, 14% of the island. Some of the telescopes you can see from a very large fraction of the island. So they've tried to find a place which is pretty well hidden, and it's certainly not up on the top of the mountain. It's tucked away, but there's no getting around it. It's 55 meters. It's as big as a cathedral or some big building like that.
I take it there are no challenges like that at the Canary Islands.
I'm completely unaware of any significant challenges. There is an environmental group there that they routinely oppose things to make sure that the processes the processes are followed strictly, to the letter. People are properly consulted, all that kind of thing. And my understanding is that the level of opposition, as it were, in the Canary Islands is very small, but it's not zero. That's for sure.
Let's see. This is one question is, Mauna Kea is at over 4,200 meters. How is it for you acclimatizing to the elevation?
For someone like myself, I don't find it a problem working up there myself, but I do run a lot and things like that. So the process is, as you drive up, there's a facility at 9,200 feet, where typically it's dormitories and a cafeteria and things like that. So people stop there. If it's the day crew, for example, all the engineers going up to fix stuff and the technicians and everything, they come up, they have the breakfast at this 9,200 foot level facility, perhaps have a meeting or something like that, then continue up to the summit, and they acclimatize for a minimum of half an hour at that level. But it's not easy to work. The one thing that I do notice is, I mentally, it's very difficult. I've tried computer programming and doing trigonometry and things like that up on the summit, and it's really difficult to do. But some people find it physically very difficult as well. And a lot of people wear cannulas and have little oxygen packs. I've done that quite a lot when I've needed to think, or when I've needed to carry 100 pounds up onto the top of the Keck telescopes, that kind of thing. So it is difficult to operate at that altitude. You can't take it lightly, and occasionally people do get sick. So you have to have processes and procedures in place. If someone falls and breaks a leg, it's a long time to get an ambulance up there. So you have to have rescue teams and all this kind of stuff you have to work out. It's quite a harsh environment to work.
It would seem like with all the remote control capability that's set up now, astronomers would rarely have to set foot up there.
For TMT and for astronomers won't go to the summit, but the day crew will go up. The engineers. Mm-hmm. And the operational model at the moment is that we will have a couple of TMT staff up there at night, but there's this long-term goal that it'll be completely remote, but it's difficult to implement. So until you've got into a sort of a steady state of operation, doing fully remote is a bit of a big deal. But the Gemini Observatory is fully remote. The Canada France Hawaii telescope is fully remote. The Keck astronomers are down in Waimea with just some observatory staff up at the summit. Subaru, I meter telescope is a little bit different. There's quite a few people go up there some nights. But if there's a problem, you have to have enough people around to evacuate someone down to a safe altitude, mm-hmm. Look after them, that sort of thing. So it's like if you have people on the summit or on the mountain, you really have to go for it. You have to make sure there's a small team, and you got your bases covered.
All right, I think there's some. Anybody else have any comments?
I went up there a few years ago, and I thought we stopped at the halfway point, and we rushed up in the Jeep, and I got up there. I'm like, "There's no problem." I got out of the Jeep, and I like 2 steps. I went, "Oh my God!" I went right back in the Jeep, and I sat down. I thought I was gonna faint. It was, man, it's something, because I go skiing a lot, and that's nothing. But man, literally, I got out of the Jeep and I said, "This ain't right," and I sat right back down for about 5 or 10 minutes. It's something up there, man.
Hey, yeah, Jack here. John Bally. I don't know if any of you guys remember John Bally, but he howls like a mashed cat when he's forced to stay at the 9,000 foot level. He says, "My house is at 10,700 feet. He lives out here above the town of Bally. So living at 10,200 or 500, whatever it is, he doesn't think he needs to stop at the 9,000 foot level.
Okay, I think we need to go on now. It's getting close to the witching hour for our meeting here. We do thank you, Dr. Warren Skidmore. That was a fantastic talk.
Thank you.
I think, yeah, we're really glad you did that talk for us tonight. It's very interesting, and
my pleasure.
Do appreciate it. Do appreciate
My pleasure.
it. Okay, thanks a lot. Okay, I think it is time for the door prizes. Is Alicia around?
Yes.
Yeah.
Hang on. Let me
yours.
post
you
the
gotta
link
set it
for
up.
let me post the link one more time. This is your last chance. So okay. You got 30 seconds to register before I close it out.
Gotta
We'll
get
have to
on
do
the
a,
stuff here, the door prizes.
I'd like to see a trip to Dr. Skidmore's facility. We could set that up with the LAAS. That'd be great.
Yeah.
Yes,
I've been there a few times, and I think LAAS had a tour once before several years ago. So the Planetary Society, we can do that without any problem.
Yeah, there's still COVID at the moment. Remember, COVID restrictions, but that won't be around forever. And so we should definitely, you should chase me up about that.
Thank you.
Yeah, well, it'd be nice to do something like that. I'd like to see that myself.
Okay, hang on one second. Let me get my.
I went to observe on a now defunct Caltech submillimeter observatory. Everybody thought I was nuts because I'm going to Hawaii in June and I packed an Arctic parka.
Yeah, first time I ever went up to Mauna Kea, I froze. The next couple of times I went to Hawaii, I had one bag full of Hawaiian and the other bag full of Arctic survival gear.
That's the way to do it.
All right.
They operate the only snowplow in Hawaii on Mauna Kea.
They used to have, when CSO was working, there was an ambulance up there parked next to CSO, plugged in to keep the engine warm. So if anybody got hurt on the mountain, they could get him in that and take them down while the real ambulance comes up and probably meet at 9,000. Is that still up there? Do you know?
I'm not sure. It was definitely there, until a few years ago. I remember having a look through the windows and to see what equipment was there and things like that. I do know that we've been working on the operations plan for TMT, and we talk about a local evacuation vehicle and teams of people that can do first aid and triage and transport a person with a broken back and that kind of thing. So we're thinking about that stuff, but we won't be around for another several years at least. So what might be there today, that red van that was there, it may be redundant by the time we come around. We'll have to think of a different solution.
As a pilot, you need to have oxygen above 12,400 feet for like a half hour Do you guys have to have oxygen up there available, or do you have to be on it all the time?
There's lots of oxygen available.
Yeah.
You know, all of the observatories, at least my experience, I'm sure Tim's at CSO, if you walk through the front door, there'll be oxygen packs and things like that, little personal things that you can carry around and you know, wear a cannula and that kind of thing.
Okay,
Okay,
it's time
so I'm
for
just
the door
ready.
prizes.
All right, so I took all the names for the 34 people that registered, and I'm going to drop them into the spreadsheet. And so the first winner is Dan Berdiansky. Benarski, sorry.
Great.
Okay.
Yay.
We win.
What I win?
Oh, you want an Amazon gift card.
Okay. Let's see. Hang on. Let's see. Where is he on here? Let me take his name off the list here. 15. Okay, got it. Next one is Mark Meehan.
Hey, Mark.
Oops. Here we go.
Is he still on?
I don't know.
Oh yeah, I see him on.
I see his name.
You're muted, Mark.
Mark Meehan, you're a winner.
He won an LAS hat. Eh.
Hey.
Okay. All right.
Okay.
Next one is Kaz. Wow, this family is hitting it big.
Buy a lottery ticket.
Yeah. Go to Vegas.
He ran a red flashlight.
Oh. Uh-oh.
Thanks.
All right. John O'Brien.
Hey,
All right, John. Hey, John.
John is still there?
I'm sorry, it was muted. Yes.
You're a winner.
I need a red flashlight.
No, you won an item from the website.
Okay. Thank you.
Joe Phipps.
Hey.
All right.
Joe.
He won an Amazon gift card.
Excellent. Thank
Joe.
you.
Hey.
All right. Oh,
Oh, new guy.
Hey, new member.
yeah, new member.
New guy. All right.
Yay.
Hold on, I have to write this last name down.
Okay.
He won an LAS hat.
Awesome. Thank you.
All right.
Annie.
Hey,
Hey,
Annie.
hey, thank you.
Any.
You got another hat.
What?
And then hat.
Who
Okay.
I didn't say a hat. Who
Kidding.
got a hat? What?
What did Annie win?
A red
She went.
flashlight.
Good flashlight.
All right.
Oh, wonderful. Thank you. Great.
How many more do we have?
2 more.
Okay.
Unless I'm forgetting something. I don't think I am.
Dan Schwartz.
Okay.
All right, Dan.
Yeah.
One item from the website. Yay.
Okay.
And one more.
All right. David.
Who's that?
Who's that?
David.
That doesn't
Which
help.
David is it?
Hang on, let me find out.
Yackerson.
It's not
Yeah.
Yackerson because
No.
Yackerson is already there. And
Let's see. Let me just see who that David is. Hang on a second.
Is he here?
David's
Galaxy?
David Moreno.
Okay, Dave.
So that would be me.
David Moreno. One of our new
All right.
Yeah.
how do you spell that, man?
Moreno.
Huh? Another new member.
Moreno.
All right.
Okay, he won a laser.
Okay.
Oh, wow.
Cool.
This
All
one.
right. And that was it. Okay.
Yeah.
All right.
Okay, so it looks like we're done with the door prizes. Now, one other thing I wanted to mention to the members, we are planning a cleanup and a little bit of a cleanup and bagging the telescope up at Garvey Ranch on Wednesday night from 7 to 10 p.m. And then we are going to be putting insecticide, a bug fogger in the facilities to be able to get rid of all the critters walking around inside there. So if anybody would like to come and help us on Wednesday night, you're welcome to come and join us on Wednesday night at Garvey Ranch.
What time?
7 to 10 p.m. this Wednesday night, the 14th.
7 to 10.
Yeah, 7 to 10. We're gonna cover up or bag the telescope, the main telescope and the cameras and everything on it. We're gonna take the food items out of the ante room and anything that could be affected by the bug bomb. We're also gonna take the eyepieces out of the workshop and items like that, because we're planning on bug bombing the workshop and the observatory and the dome itself, the dome area itself. So that's what we're planning on Wednesday night, Thursday morning. So we need to do that. So one of the first things we need to do, and then, like I said, we'll try to get the 8-inch telescope up and operational sometime in early August. So that's the near-term plan right now. And if anybody wants to come out on July 21st for the bring a telescope out on July 21st for the scouting event, that would be very helpful to have that, because we're gonna have all these scouts out there and they will need to look through a telescope to identify things. That is, of course, cloudy, clear weather. We want to have clear weather, although from Garvey Ranch we can't see much, but at least we'll have something for them to look at. Okay, so any other items that I missed at the meeting here tonight?
Is there a word?
Nothing that you missed, but let me just mention to the new members.
Yes.
I think one of you got maybe a gift card, but if you're buying anything on Amazon, there's I don't know what you would call it, a program called Smile. And if you sign up on smile.amazon.com, and you can choose the charity of your choice, and so it would be LAIS, and we are one of the choices. So any items that you buy, and some of them are not eligible, but any eligible items, a little bit goes to us as well. And it's starting to pay off. We started a couple of years ago. People are finding out about it. If you just change it to Smile as your default go-to, other than that, everything else that you have set up in your Amazon account would be the same.
Is there a word on Garvey Ranch whether masks are going to be required on either this Wednesday or at the telescope?
No, because the telescopes are going to be out on the field, and everybody that's going to be doing the cleanup, most of us have been vaccinated already, so we're okay on that.
Well, that's confusing. You're talking about this coming Wednesday? Yes. Were you talking about this coming Wednesday, Greg, or the 21st?
I'm talking about both, actually. So.
Well, this coming Wednesday is not really an event. It's a cleanup. So
yeah.
All the people that are there have been vaccinated. I guess masks would be optional.
Okay.
Yes, and
then
same
for the 21st, I believe. I don't.
Yeah, the 21st is out. We're going to be setting up outside to begin with, so that's majority what we're going to be doing. The restrooms are available, and if you're concerned, bring disinfectant wipes, whatever you need to take care of any concerns. Okay.
Bring a mask if you want.
What was that?
Say bring a mask if you want to. I think there's going to be a lot of scouts there, young scouts. So.
Oh yes, on that one. Yes.
On the 21st, yes.
Yes, on the 21st, yeah.
Yeah, they may not be vaccinated if they're too young.
Yeah.
That's great.
Okay, well, anyway, I think we're okay on the meeting. I just wanted to make one little comment to Alicia. Yes, we did get the link for the two Amazon gift certificates that Carol won, and she's planning on buying a resin crocodile float for the pool to prevent the duck to help prevent the ducks from landing on her pool.
That's not what I expected, but okay.
That's not a laser pointer.
No,
ducks.
I thought that would be a neat little thing to say. If she gets ducks on her pool and the pool guy says the ducks are making it dirty.
It's costing me a fortune. Well, that's a new one.
A fortune to clean the pool.
That is true. I feel her pain on that one.
Yeah.
I feel her pain.
So we should probably end recording, and then we can still hang a bit.
Right. Yeah. So
Yes,
okay,
it's
I'll
going to be
stop.
9:54, and I will go ahead and officially adjourn the meeting for tonight. I officially adjourn the meeting at 9:54 p.m. Thanks a lot, everybody. Thank you. And